This meeting is being recorded.
The next concept that we'll look at from chapter 14 has to do with the change of concentration over time. And we can calculate this using what's called the integrated rate law. So in the last section, we looked at the order of a reaction with respect to each reactant, and we solved for exponents to determine the order of reactions. So note that there are different integrated rate laws depending on what order a reaction is, because for example, here, our first order reaction has a certain rate. So we saw that a rate of disappearance for a first order reaction could look something like this, where we have some constant. Remember that negative value indicates a rate of disappearance times this concentration of A. So again, this would be a first order rate law or rate equation, right? Rate law, rate equation. And if we were to integrate this, we could find the rate of disappearance over time. So this over here is an example of how that could look if we were to designate A sub 0 as our initial concentration of A. A sub T would then be the concentration of A after whatever amount of time has passed during this reaction. And we know that we have that negative value because it's going to indicate rate of disappearance. And then we have our K, our rate constant. And then over here, the T tells us how long has passed, how much time. So we have to make sure that we match our units of time with our K values. So we'll make sure to do that. So match units of K and T for time. So when we take a look at this example down below, sample exercise 6, we're going to use this form of the equation right here. So if you know some rules of calculus, when you have something divided by something, in the expanded form, that's the same as, say, we had natural log of a sub t subtracting a sub 0. So that's where we get this other form down here from. So let's take a look at example 6 and see if we can work through the concentration over time for a first order kinetics reaction. So we're told here that we have decomposition of this insecticide in water. We're given a temperature. The only reason that we're given the temperature is because rate constants, like this one right here, 1.45 per year, are generally temperature dependent, or they're always temperature dependent. So we're just given that temperature to show you that the temperature is in average that same 12 degrees Celsius. So that sets us up for success in this problem. We're given some information that on June 1st of 1 year, the concentration or some amount washed into a lake, and the concentration ended up being 5.0 times 10 to the negative 7th grams per cubic centimeter. So then we're asked in part A here, what is the concentration on June 1st of the following year? So exactly the time would be rather 1 year has passed. We're told that our initial concentration of A was equal to 5.0 to the negative 7 grams per cubic centimeter. This is generally a unit, derived unit used for density, but we can also use it for concentration. So let's see here. And we're also given our K value, 1.45 per year. So let's take a look at the first order rate law equation. So the natural log of A after some time has passed, that time t, would equal negative, and we're going to plug in our K here, so 1.45 per year. So negative K, T is exactly 1 year, so that unit will cancel. So then we have the rest of the equation was plus the initial natural log of the initial concentration of A. So actually, let's just plug that in here. So that'll be the plus the natural log of 5 times 10 to the negative 7. All right. So if we were to plug in these values here, we're going to just carry down natural log of A sub t. That's going to equal negative 1.45. Just combine these here. Plus the natural log of this value turns out to be negative 14.51. We can then combine like terms here, and we get negative 15.96. This will equal the natural log of A sub t. And if you do not recall how to reverse a natural log, we can do so by taking the e of each side here. So if you, on your calculator, type in e, and that's raised to the negative 15.96, that will give us the concentration of A after 1 year, after time t, and that comes to be 1.2 times 10 to the negative 7 grams per cubic centimeter. So that's our answer for part A. In part B here, we're asked how long will it take for the insecticide to decrease to a specific concentration. So now we're going to use the same equation, but we're going to plug in the natural log of this final concentration over here. And then remember we have negative k, so 1.45 per year times our time, which we're going to solve for now. So we're going to have just time t here, and that's going to be plus the natural log of our initial concentration given in the question above. All right, so we know the natural log already of this was negative 14.51 from above. Now we just have to solve over here. So the natural log of 3 to the negative 7th gives us negative 15.02. So this equals negative 1.45 times t. And we can again combine like terms. So I'm going to add this amount over here and that same amount over here. So I get negative 0.51 will equal negative 1.45 times t. So times t. And then we just divide by this on both sides per year. So we know that our time will be in units of years, and 0.5 divided by 1.5 gives you approximately 0.35 years. So just over a third of a year for that concentration to decrease to that amount.